Alrighty, so we're going to do a quick overview of conic sections. So we're going to be talking about all four conic sections and how do we recognize which type of conic we have based on the equation, and also just some general how do I work with each one of these. So just big picture idea. So a nice overview. So it's going to be a pretty short unit, but we want to make sure that we're ready to deal with conic sections, easy for me to say, moving forward. So 10.2 is the first section we're going to be looking at in chapter 10. We're going to be talking about parabolas, and then 10.3 is also going to be part of this video, which is going to be about ellipses. So we're going to kind of deal with both of those at the same time. So how can we recognize which conic section it is? How do we write them in standard form? And then what kinds of real life applications are we actually using when we look at these? So a conic section is just defined to be the intersection of a plane and a double cone. So if you think back to last year in Algebra 2, there's actually 4 different types of conics that you can have, and I have some pictures for you on your additional notes as well that we'll take a look at. But the 4 basic conic sections are circle, parabola, ellipse, and hyperbola. Always interesting to hear how people pronounce some of these. So basically how you slice a cone in different ways will give you these different shapes. So this is going back to the Greeks and basically 500 BC. So this is kind of ancient mathematics that we're talking about when we look at these. So I want to show you some pictures so you can see the relationship for that. So a circle is if you slice that cone parallel to the base, so we get a circle shape on that cone. Ellipse is if we take that plane and we make it not parallel, so just intersecting one of those ends of the cone. A parabola is if we are going in that direction, so something that's closer to parallel with the height of the cone. And then a hyperbola is actually parallel to the height of the cone. It intersects both the top and the bottom part of the cone, so that's where we get those two sort of parabolic shapes. So just slicing a cone in different ways gives us what we call conic sections, so sections of a cone. That's where that name comes from. Every conic section, too, can be written in a general form. Very similar to like the general form that we talk about for polynomials, right? We have the a, the b, the c, the d, the e, the f. Those are all coefficients, number values. And notice we have x squareds and y squareds, and we have just x and just y, and we can have xy terms as well. So any basic format of this, depending on what your coefficients are, will help you determine what kind of conic section you have. So over the course of our quick little review, we are going to be talking about how do you tell which conic it is based off of the equation. So we'll be talking a little bit about that as well. In the formula of the 4 basic conic sections, if the plane does not pass through the vertex of the cone, if it does pass to make a conic section, if it does pass through the vertex of the cone, then we get things that they call a degenerate conic. Sounds just very sad, but a degenerate conic means it's not actually one of the conic sections that that we know and love. So it's something that would not be in that classification. So sometimes if like look at these are just 3 examples. If it goes right through where the 2 parts of the cone meet, it intersects at a point. That's not a conic section, right? So that's not something we'll be looking at. If it is right along the edge of the cone, that plane intersects. It actually intersects and makes a line. That wouldn't be a conic section either. And then if you put that plane right through the vertex parallel to the height, right there, it actually makes 2 intersecting lines. That would also not be a conic section because that's not going to be one of the 4 shapes that we're talking about. So it can't go through the vertex at all of the cone, otherwise it's not a conic section. So that's the what they call degenerate one. So just realize that when we're looking at these, we're talking about our big 4. All right, so let's talk about parabolas. So I'm going to do parabolas and ellipses today. A parabola, this should not be a super big surprise to you, is a set of all points that are equal distance from a fixed line, which they call the directrix, and a fixed point called the focus. So equal distance from a point and a line makes a parabola. So there's some really cool videos to be able to watch to see how those are constructed when we go through and look at that. So it's just all those fixed points. The vertex, we're very familiar with this. We've talked about that. A parabola is the midpoint between the focus and the directrix. It's on the axis of symmetry, and we know that axis of symmetry goes right through the focus and the vertex. It cuts that parabola in half. So I have a picture that we're going to talk about so we can see what that looks like. So I just put it up in the important vocab area to describe what we just talked about. So here's that vertex, that HK that we've talked about before, halfway between the focus and the directrix, because every single point on this parabola is equal distance from the focus and this directrix, this horizontal line. So this distance and that distance would be equal for the vertex as well. So notice they picked a couple points on here to describe that. So if you're here on the parabola, the distance to the focus and the distance to the directrix is always going to be congruent. That's how you make a parabola. And there's a lot of really cool things that we can do with that in real life situations. So we'll take a look at some of those at the end of this. There's two different ways that you can write the equation of a parabola, standard form. So we can have a vertical parabola. That means one that's opening up or down. So a vertex at HK, this should look very familiar. Standard form, sometimes people call this vertex form because it's the easiest way to be able to see what the vertex is. Remember that leading coefficient, the A value, tells us about the steepness, so that vertical stretch or compression. It also tells us about the direction it opens, right? So if it's positive or negative. So we have that same idea. You can also have a parabola that's horizontal. So a vertical parabola means I'm opening up or I'm opening down. A horizontal parabola means it either opens to the right or it opens to the left. It has a vertex at HK, same thing, but notice the H is on the outside and the K is on the inside. When you're solved for X, everything switches. Remember that symmetry over Y equals X. It's like it's finding the inverse. So the X and the Y are switching roles here. So just have to be careful that we realize that. But the A value is still going to talk about that horizontal now stretch or compression and the direction of opening. If it's to the right, the A has to be positive. If it's to the left, the A would be negative. So just like if it's opening up, the A is positive. If it's opening down, the A is negative. Very similar kind of conversation. So we can have either way. So we have two different types of parabolas. The first one, the y equals, is definitely a function. The x equals, definitely not, right? Because it would not pass the vertical line test. All right, so what we're going to do is practice one of each, just getting into the form and being able to recognize why this is going to be a parabola. So here is a kind of a standard setup for an equation that's a parabola. How do I recognize that it's a parabola and not any of the other conic sections? Notice how many square terms you have. So if you look through your equation, I only see one square term, and that is the key to be able to tell that this is a parabola. There is only one square term. All of the other conic sections, circles, ellipses, hyperbolas, all have two square terms. So that's the first and most important thing to look at in this general form. How do I know it's a parabola? One square term. Okay, now how do you know if it's a parabola that's horizontal or a parabola that's vertical? Look for which one is not squared. I'm going to go back to the formulas for a second. In the vertical parabolas, this top one, the y is not squared, and in the horizontal, the x is not squared. So that's what I need to look for here as well. Which one isn't squared? Well, the one that isn't squared is the y. So since the y isn't squared, this is going to be a vertical parabola. This is going to be one that either opens up or down. So that's the other thing to kind of look for. Which one isn't squared? So the one that's not squared, that's going to be the one we want to solve for. So if you think to the formula that we want to look at, we want it in that vertex form. I need to get the y by itself then. So my first order of business is I'm going to go ahead and move the 4y to the other side, and I'm going to move the 13 back over here so I can have the y by itself to get ready for whatever I need to do. So I'm going to add the 4y, so 4y equals, and then I have x squared minus 2x, and I'll be adding the 13, right, to each side. So add 13 and add 4y, just to kind of move your terms around and get things in the order that we need them. Now, to get into vertex form, it's that whole complete the square that we did before. We've done that for all the other, when we talked about parabolas earlier in the year in chapter 2. So we're going to complete the square to get it into that nice user-friendly form so we can see where that vertex is. So right now, this is definitely not factorable into a binomial times itself. So this is where, remember, your leading coefficient needs to be 1. Thank goodness it is. We're going to find that new c value in here that will make this a perfect square trinomial. The 13 is most definitely not what we need. So what we're looking for is what do we fill in for that box. Now remember, if we do something here, we're going to have to do something on the outside to counteract that, right? Because we want to make sure we're not changing the value of this. We're just trying to change how we're writing it. So we have it in vertex form. All right, so do you remember how to complete the square, how to find that box? What's ever in the box? It's take the middle term, the b value, divide by 2, and square it. Perfect square trinomial means it's doubled. They're both the same. So we're undoing that. We're figuring out what had to be doubled, and then we have to square it because when we do our FOIL, we'd be multiplying it times itself. So our b value in this one is our -2. Remember, it doesn't really matter the sign because you're going to square it anyway, but let's go ahead and see what we get when we do that. So we're going to divide by 2. So that would be -1, and -1 squared would be 1. So what I'm putting in here is a 1. Okay, so what I just did is I just made that side of the equation 1 bigger. So technically, I'm going to get rid of this for a second. Technically, I should also add 1 on the other side as well, right? Because if I do something to one side of the equation, I need to do it to the other. But now, again, I want to solve for y ultimately, so I'm going to go ahead right away, and I'm just going to subtract that 1 to move it over to the other side. So a lot of times I never even show the 1 on the other side. I just automatically do on the outside whatever the opposite is of this. So if I made it 1 bigger, I got to make it 1 smaller on the outside to counteract that. It's just the moving it over from the other side. So you're doing something to one side of the equation and to the other. Let's take care of that right away. I can't change the value of it. All right, so now why did this work for us? Well, now I can factor this trinomial. That factors into x minus 1 times x minus 1, which is x minus 1 squared, perfect square trinomial. On the outside, just do the arithmetic. So that would be a plus 12. So we're almost there. All we need to do now is deal with this 4. Notice I didn't really do anything with that because that's going to be part of that a value that I'm going to have out front. So I'm going to go ahead and divide everything by 4. So every single term in the entire equation has to be divided by 4. I guess for the first one, I'm going to think of what this coefficient would be then. So 1/4 times x minus 1 squared, and then plus 12 divided by 4 would be 3. So make sure you divide everything. So completing the square, making that perfect square trinomial is going to allow us to see what that vertex and everything is going to be. All right, so let's kind of analyze what we have here. So our a value is 1/4, which means this opens up. So it's opening up. That means the vertex is a minimum, right? So it's a minimum value, and that's important to think about in real life application if we're trying to do whatever we're talking about here. Because it's a fourth, has been vertically what? So if it's less than 1, it's been vertically shrunk. So it's a vertical shrink. Oh, I should just say vertical shrink. And then where is your vertex? What is your HK for this one? Well, H is always in with the X, so 1 and then 3. So our vertex is at 1, 3. The axis of symmetry, we could go even further here where that fold line is. The axis of symmetry would be X equals, remember it goes right through the vertex, so X equals 1. So the whole idea of being able to solve and find this vertex form is to be able to say all this about it. It's really hard to do that when we look at this general form, what we started with. It's like, what does that mean? But now I can tell, hey, it's a parabola opening up. I know that it's been vertically shrunk. It's flatter than what it was before. I know the axis of symmetry and the vertex. I could make a really good sketch and do a lot of different things with it. All right, we'll try one more parabola and then we'll get on to applications. So let's take a look at how do we know that it's a parabola. I'm saying that it is, but how do we know? Do you remember what you look for? How many squared terms? So again, I only see one squared term. So that means it's going to be a parabola. So we're really going to emphasize that. That's how I know it's the only conic section that has only one square term. Now, which term is not squared? Well, if I look through, it's the y that's squared, so the x isn't squared. So if the x isn't squared, that means, go back to my formulas here, that means I'm looking at the second version here. It's the x equals. This is a horizontal, and I know that because it's the x that's not squared. So this is going to be a horizontal. It's either going to go open left or to the right. So it's going to be one of those. So again, same kind of strategy. I'm going to do some sorting and organizing. I want to solve for the thing that's not squared. So I'm going to move the 8x to the other side here. So I'm going to add 8x and just get things kind of set up. Now remember, when you're completing the square, if you have a leading coefficient like that y, if it wasn't a 1, you would have to deal with that first, pull it out. Thankfully, I just have a 1, so I'm not going to worry about that. So I have a y squared plus 6y. I'm going to say plus blank. My 25 is going to be on the outside. And whatever I do inside, I'm going to have to counteract that. So we'll talk about our different options. All right, so I'm going to give you a moment. Can you pause the video, see if you can fill in the blank? What will we need there to complete the square? And what are you going to do to counteract it? So pause the video and see what you can do with that. So remember how we complete the square. We take half of the middle term and we square it. So half of the middle would be 3. 3 squared would be 9. So it looks like I'm adding 9. Okay, so now remember, if you add 9, I just made that right-hand side of the equation 9 bigger. Okay, so I have to counteract that. I can't do it to one side and not the other. So one option is to add 9 on the other side. But then again, I'm going to have to solve for 8x anyway, so I'm going to have to subtract it. So I would go ahead and just subtract 9 on the same side right away. So that's your option how you want to do that. All right, so now let's see what we've got left here. So we have 8x equals, let's go ahead and factor the trinomial. That would be y what? So go ahead, take a moment, factor that trinomial. So what multiplies to 9 adds to 6? So that would be y plus 3. And then on the outside, we're going to find our new k or h value, actually, and that would be 25 minus 9, so 16. And then it looks like all we have left to deal with is that coefficient of 8. Leave that to the very end so we don't have to deal with yucky numbers when we're trying to do that, complete the square. So remember again, I'd write that coefficient 1/8, and then we have our y plus 3 squared, and then plus 2. Tried to pick numbers that worked out pretty well. Okay, so now remember, this is horizontal. The a value is 1/8, which means we're dealing with a parabola that was a positive number. So that means this parabola is going to open to the right. It's positive, so it's going to be a parabola that's opening this direction. And we have that horizontal stretch, actually, is what it's going to be ending up happening with that, because it's less than 1. So we have a horizontal stretch. Our vertex, let's talk about the vertex. This is kind of tricky for people. You got to remember HK, but the H now, because this is horizontal, is on the outside because it's the X value now. So the X value, that shifting left and right, is on the outside. What's in with the Y is always going to be the vertical shift. So the vertical shift is actually on the inside. They're just flip-flop. Remember, that's what inverse means. They're in the opposite location. So that means my H value is actually the 2, and my K value, careful on that, if it's plus 3, that comes from minus a negative. So -3. So this is the H and that's the K. Just be careful that we're going in the right direction. All right, so lots of different things that we can do with parabolas. We'll talk about a couple different things here, whoopsie daisy, just to show you. So when we talk about how we use parabolas in design, because of that equal distance, it's a very strong, strong shape. So things like the Golden Gate Bridge, they use it to design that shape, and so we can even see that in some of the bridges around here where we have that sort of parabolic, they call it, shape to be able to construct the support beams. It's also used in astronomy. A lot of telescopes use parabolic dishes, meaning the shape of the dish is a parabola, to be able to collect radio waves because of that equal distance and going to that focus point. So it's a really common thing in design to see those parabolic shapes. So it's kind of cool, and you can actually do a lot with those. All right, so let's talk about ellipses then. We're going to finish up and do a couple things with the ellipses in this part as well, so we can deal with what we need to for these. Let's actually, I think what I'm going to do is I'm going to stop the first part of the video and do a separate one for ellipses, just to make sure this one doesn't get too long. So I'll do a separate one for ellipses. So we're going to end this one with just making sure we understand the two different forms for parabolas.